Okay, we've just gone over the surveys. If you have more to add, you can continue to adjust your response and add new details on the surveys for all the classes, I think, until Friday night. And then they close. The instructors don't see the survey results until after final grades are submitted. So if you're worried about offending someone with your feedback, don't worry about that from the standpoint of it affecting your grade, at least. All right, a couple of announcements just as a review. Homework 13, the last assignment is due on Friday by 5 o'clock. And then the class that we'll have on Friday is going to be held online. This will be our last class meeting face-to-face. Of course, we're going to have the final, but this is our last class meeting face-to-face because class on Friday is going to be recorded and posted online. And I'll email you the link for that. All right, so regarding the final exam, that is the last exam day, the last exam slot, Friday afternoon. We've got 2 hours, and I plan to make it probably about twice as long as a normal exam. So you'll have proportionally more time than questions compared to usual, because I'll write it with about 100 minutes in mind, but you've got 120 minutes to solve the exam. So my hope is that nobody feels time pressure during the test. It's going to be comprehensive, so that means questions can come from the first part of the course when we're talking about closed conduit flow through pipes. And so you should be prepared for questions from any of the sections of the course, but there will be proportionally more points on the recent material that you haven't been examined yet on. And so the stuff that we've had since the second midterm, there's just going to be more of an emphasis on that material. You should bring in your computer with Water Gems and Excel. You may or may not have a question where I ask you to use Water Gems, which hopefully by now everyone feels really confident and comfortable after the project. So there may be a final exam question related to Water Gems. In addition to the formula packet that I'll be giving, you can also bring in 3 pages of notes. So if you have your previous formula sheets from earlier exams, you can just use those. If you want to prepare something new, you can, but it can be letter-sized paper, front and back of both sides of that. And so any questions about the details of the final exam? Now, on the subject of the project, I'm more than halfway through grading those, and I hope that I'm going to finish the rest of them this evening or perhaps tomorrow morning. So the vast majority of your points are going to be known in advance, and if you look at the grade book average that's shown there is live. As long as the numbers are there, then the weighted average just takes into account the points that it knows about. Of course, there's no assumption made about your final exam grade yet, but it'll give you kind of an idea of where things stand as you go into the final exam. Any questions before we continue talking about sewer design? All right, so this is what we were looking at last time. This idea that when water is flowing through a circular conduit, the geometry is a little bit tricky. And besides that, not only is the geometry tricky, but we also have to account for a difference in the N value if the pipe isn't flowing full. And the reason is that normally when we have a circular pipe and we give it an N value, we assume that the water is all the way to the top and the amount of resistance that's being imparted is due to a full conduit. But if we only have a partially full pipe, then there's going to be more wetted perimeter relative to the cross-sectional area than there would be for a full pipe. So we have to adjust the N value, and that's what this nomograph does. Is it tells us both how we can adjust the N value if the pipe isn't all the way full. So the vertical axis on this figure is the flow depth Y compared to the pipe diameter D. So if we know that the pipe is flowing, let's say 60% full, then we would go to this curve, and if it's flowing 60% full, then that tells us that the end value is 1.2 times the normal end value that it would be if it was flowing full. So for instance, a concrete pipe has a typical end value of 0.013. That's what the manufacturer would tell you. But that would be its end value if the water is flowing full. So if it's flowing 60% full, then you'd have to multiply the 1.2 times 0.013, which is the end value under normal circumstances. Okay, so last time we went through this nomograph method and determined the full flow rate using Manning's equation. And then once we knew the full flow rate, what we did is we multiplied it by the ratio of Q to Q full. So I showed you in class last time the nomograph method, and we also did a paper version of the angle method. What we'll do is we'll also solve that with a spreadsheet, and that's the template file that I mentioned for you. Did you find it on Blackboard? Yeah? Okay. So let's take a look at that. Let's solve this same example using Excel, and I'll open up that template file as well. Okay, so in the sewer design procedure, oh, I'm sorry, hold on a second here. No, I've gotten confused. The template is for a different example. We won't use it. We won't use it for this one, although we could. I mean, because effectively what we're doing is using the geometric parameters, you know, starting with a guess value of theta and setting the right-hand side and the left-hand side equal. We've got a different example we're going to use the template for, but maybe if we've got the time, we'll come back and validate what we had solved on paper with this example. All right, so let me show you how we do use Excel and why that template is set up the way that it is. The first thing that we do is determine whether we're using SI units or British gravitational units. And if we're using this, you know, standard English imperial units, then 1.49 is the coefficient that goes on the Manning's equation. And if it's SI units, then we just use 1. And so we rearrange Manning's equation for a circular pipe. So in terms of the diameter of a circular pipe, we can express both the area and wetted perimeter in terms of D for a pipe that's flowing full. So size the pipe diameter for max flow. What we want to do is solve for what diameter is needed so that the water's all the way at the top of the pipe when the conditions are maximum flow. And by the way, do you remember, this is a bit of a review, but do you remember what is the hydraulic radius when you have a circular pipe that's flowing full?
D over 4.
That's right, D divided by 4. So the hydraulic radius, remember, is area divided by wetted perimeter. And the area is pi d squared divided by 4. And the wetted perimeter is pi d. So if we cancel out the pi, we cancel out the d in the denominator and one of them in the numerator, then that's just d divided by 4. So that's what's going on in the background here where we're doing these substituting and rearranging for d. The d parameter is just assuming full flow. This first part of our Excel procedure is going to be solving for what diameter is required if we wanted the pipe to be all the way full at the maximum flow condition. So remember, max flow is going to be sometime during the day that we expect there to be the most water entering either a sanitary sewer, or it could be that we use the same process for sizing a storm sewer if we knew like the peak flow rate that is coming out of a parking lot during a storm. Now, we have to round up to the nearest actual pipe size, because when you solve for D, you'll get something like, the pipe should be 14.85 inches in diameter. And there isn't going to be a pipe that's exactly that size. And so you need to be conservative and make the pipe a little bit bigger. You'd round up to the nearest commercially available pipe size, and then you'd evaluate with that actual pipe diameter that's being used what would be the normal depth of flow under those conditions. And so it won't be all the way to the top. Y will be less than D in the second step. So here is where we've rearranged Manning's equation, have a left-hand side and a right-hand side. And the reason why we do that is the right-hand side will be constant. That'll be known. And the left-hand side will be unknown based on theta. So we'll have to start with a guess of the angle, where the theta that it's talking about, remember, is the angle that the water line makes if you were to start at the center of the circle and draw a triangle down to the water line. So theta is increasing as the water level goes up. So if it's above 50% full, then you're going to have more than pi theta as the angle, because those legs continue upward beyond the halfway point. Okay, so back to this procedure. We solve for theta when the left-hand side and the right-hand side of this equation are equal. And then once we know what the angle is, then from that we can determine the flow depth y. So just, theta can be determined based on the ratio of the depth to diameter, or if you know theta, now you'll find the flow depth by knowing a certain pipe diameter. So this is going to be built into that template, but we also want to consider what's happening in the sewer under conditions other than maximum flow. We also want to evaluate what is the depth when you've got the minimum flow going through the pipe. And you want to also determine what's the velocity when there's the minimum flow. And optimally, you'd like to see that the velocity in the sewer stays above 2 feet per second. Because if it does, then the sewer will have a self-cleansing effect. And if it falls below 2 feet per second, then the sediment and the solids that are in the sewer can settle to the bottom of the pipe. They can stick to the bottom of the pipe, and the pipe can begin to fill with materials. And so here on the left, you can see a nice clean pipe that experiences regular self-cleansing. And on the right-hand side is a pipe that's been clogged over time, both because maybe they didn't have a grease trap at a restaurant, or it could be related to the quality of the water that's flowing through there, but it could also be related to inadequate flow velocity during extended minimum flow periods. Okay, so let's say that we have a concrete sewer pipe that needs to carry a maximum flow rate of 2.5 cubic feet per second. And we expect that it's going to be laid out on a 0.75% slope. And then during the minimum flow periods, the flow rate's going to be as low as 0.45. So just to simplify things, what we're going to do is stick with an n value of 0.013. We could make our answer about the flow depths a little more accurate by accounting for the varying n value in this, but just as a first exposure to this design process, let's neglect the slight variations in n value that can occur for partial flow depths. So again, we're going to step through this process of finding out what diameter is required, rounding up to the nearest available commercial pipe size, finding out what is theta, from that determine the depth, and then evaluate how does the pipe behave at the lower flow rate. Okay, so now this is the point that we will take a look at this spreadsheet. So in our problem that we're working on, we've got traditional units, cubic feet per second. And so what that means is we're going to use x as 1.49. So that's the coefficient that we put in front of Manning's equation if we have traditional units. The Maximum flow rate we have to accommodate through the pipe is 2.5 cubic feet per second. And then the minimum flow rate is 0.45 cubic feet per second. And then the slope, 0.75% means 0.0075. Or in other words, we have 0.75 divided by 100. 0.0075. And then the n value here, 0.013. Now, if we wanted enhanced accuracy, what we could do is, after we go through and iterate this a couple of times, we could also refer to this figure to update the n value. For now, we'll leave it as fixed. Okay, so what is the pipe diameter that's needed according to Manning's equation, assuming that you've got the water filling the pipe all the way to the top? So we're going to solve this, Manning's equation, which has been rearranged for D. Okay, so it's equals 1.55 times the flow rate maximum, and I'll anchor that reference, although I don't know that I necessarily need to. I guess it doesn't cause any harm. Multiply it by the n value, divide by this coefficient 1.49, and in the denominator we're also multiplying it by the slope to the power of 0.5. And then everything that's inside of those parentheses is raised to the 3/8 power. So we're not yet referencing this minimum flow rate. And this is going to solve for the diameter in feet. Oh, it looks like I've maybe got an error someplace in my formula. Let's see.
You have to put parentheses around your fraction on the exponent.
Yep, that's it exactly. Thank you. Good cut. Yes, because otherwise it would take it to the third power and then divide by 8. Yeah, okay. Order of operations. Okay. 0.924. Yeah, that's right. So that's how many feet it should be, which in inches, if we multiply by 12, says 11.09 inches. And they don't sell pipes that have a diameter of 11.09 inches. The best we can do is a 12-inch pipe. They do make that. So we'll use the actual diameter for construction of 1 foot. Any questions so far? Okay, now obviously since we only need 0.92 feet and we're going to use 1 foot, then the flow depth isn't going to be all the way to the top. And it's not just as easy as saying the flow depth will be the ratio of the diameters. It's not that simple, because the flow area is related to the diameter squared. So we do have, and there's also other effects. So we need to rearrange this equation, because we're going to use this formula, and here where it says the right-hand side, we're talking about Manning's equation that we've rearranged to isolate all of the constants on the right-hand side of the equation. Okay, so the right-hand side is just going to be, I don't think I'm going to bother anchoring these references since we're not copying and pasting for other iterations. So I'll just have the n value multiplied by the flow rate maximum divided by the units coefficient times the slope to the power of 0.5. Okay, so 0.252 is what I'm going to keep changing the theta, which is going to influence the area and the wetted perimeter. I'm going to keep changing guesses of the angle until the left-hand side equals this right-hand side constant that I've just found of 0.252. Okay, so I don't know what the angle is to guess. Let me just start with maybe an angle of 1 radian. So 1 radian would be pretty shallow. I know it's going to be deeper than that because I haven't reduced the pipe diameter too much. You know, I'm sorry, expanded. I only needed it to be 11 inches and I'm making it 12. So the water's probably going to be close to the top. But let's just say I start with a guess value of 1 radian, which isn't even halfway depth. And then I'm going to calculate the area and wetted perimeter based on that guess of the angle. So the area is, parentheses, the angle minus the sine of the angle times the diameter actual squared divided by 8. Okay. Once again, looks like I need to be more careful about my parentheses. There we go. No, the parentheses should be here. Really off my game today. Okay, so let's see. Squared divided by 8. Yeah, okay. So this time I don't want parentheses around this because it's not to the 2/8 power. It's squared and then divided by 8. All right, let's see if that's more like it. Okay, so I've got some area based on the angle. Let me write the wetted perimeter in terms of the angle. So that is going to be the angle times the diameter divided by 2. And so then the left-hand side of this equation is area to the 5/3 divided by wetted perimeter to the 2/3. So area to the power of 5 divided by 3, in parentheses, divided by wetted perimeter to the power of 2/3. So that's the left-hand side of the equation, and it's not going to match the right-hand side of the equation, not yet, not just when all we've got so far is a guess value of the angle. So the difference between the two, I'm going to do the right-hand side minus left-hand side. And the reason why I want to know the difference is I'm going to execute goal seek, and my goal is going to be to take the difference down to 0. So that's how goal seek will know when to quit, is it's going to keep playing around with this angle until the left-hand side, which is calculated, is equal to the right-hand side constant. Okay, so let me try that goal seek here under data, what if analysis, goal seek. Our objective is that we want to set this difference to 0 by changing the angle. As soon as I click OK, very quickly it's going to substitute a lot of different values and then stop when it finds something that's close enough so that the right-hand side and the left-hand side are equal. Okay, so what it's suggesting is 3.88 radians is the angle. And that makes a lot more sense than 1 radian did, because the water's going to be above halfway, which would be 3.14 radians. Okay. So the difference is 0, and now the flow depth y, we can use the angle that we've just calculated and this formula to determine how deep the water is going to be in that pipe. So it is the diameter of 1 foot divided by 2 times 1 minus cosine of the angle divided by 2. Now, lucky for us, Excel is expecting to see radians in these sine and cosine functions. So we don't have to convert it from degrees to radians because radians is what our formula gives us and radians is what Excel is expecting. So we can just put those angles in directly. So for the flow depth, it's saying 0.651 feet is going to be the depth of flow. Okay, so now remember I mentioned that so far we've just been using a constant n value. We wouldn't have known what to use for the actual n value yet because we didn't know what was the ratio of depth to diameter. Now we can adjust it a little bit better. So we've got a flow depth of 0.681 feet and the diameter is 1 feet. So in other words, the depth to diameter ratio is 0.681. So if we go up here, 0.6, not quite to 0.7, but 0.681 maybe is, looks like 1.17. So if we use 1.17 as the n to n full ratio, then we could have an adjusted n value, 0.013 times that correction factor, 0.01521. So as soon as I change this, everything else is going to be changed as well. 0.01521. So that'll be the n value when it's flowing partly full. Now, that says that the required pipe diameter is closer to a foot. It didn't luckily go over 12 inches. So we're going to stick with this actual flow diameter of 1 foot. The right-hand side has changed because now the n value is different than it was before, slightly higher. So we need to goal seek again because we don't have a zero difference between the left-hand side and the right-hand side. So if I go through the process of goal seeking again, what if analysis, goal seek. So it's the same thing where I want the difference to 0 by changing the angle. And we let it do its thing. And now instead of saying 0.681, which was the previous depth, it's saying 0.773. So because the pipe has proportionally more wetted perimeter when the water isn't all the way to the top, then it's going to be 0.773. But now that we have a new flow depth, we need to adjust our n value slightly. We'll just do it one more time. So if it's 0.773, the difference won't be so significant this time. 0.773, then our true correction factor is probably more like 1.14 instead of 1.17. So if it's 1.14, then that means the n value we should use is the 0.013 multiplied by this correction factor. So 0.01482. 0.01482. Okay, so we've got an adjusted diameter. We have to goal seek just one last time because we're already pretty close to that difference being 0. But let me do the goal seek where we want that difference to be 0 by changing the angle. And it goes through, and so it's going to be about 3/4 full. It's suggesting that the flow depth is 0.756, and at this point I couldn't probably get a more accurate estimate of that correction factor than I've already got, where I said 1.14, probably about the same. So this is going to be my final answer of the flow depth when we have the maximum flow condition. So let me just write a note here. This is the flow depth at Qmax where we have iteratively corrected the n value for partial depth. So this really is a good estimate of what the flow depth is going to be. Okay, so then what's happening at minimum flow? We've got that 1 foot diameter pipe, And minimum flow is when the conditions are 0.45 cubic feet per second. So again, we have to evaluate what's the right-hand side of this equation when we've got the minimum flow. So the right-hand side is going to be the n value. So that's 1.49. Oh, I'm sorry. No. The n value that we're going to use is, we'll start with this one. There's going to be a different n value because it's going to be lower. I'm going to call this n min flow because I don't want to change this because then it would change the flow depth at the max flow. So the n value at the minimum flow, let's start with a guess of 0.013, and we'll have to do that correction thing. So this would be the n value if it was all the way full, and we know that it won't be. Okay, so then the right-hand side is going to be n times q under the minimum flow conditions divided by x times s to the 1/2 power. Okay, so that's the right-hand side of the equation. Theta, again, I'll just start with a guess of 1 radian. And then the area and wetted perimeter as a function of that guess. Here I'm going to say that the area is theta minus the sine of theta times the diameter, which is still 1 foot, diameter squared, and then all of that is divided by 8. Okay, so I've got a cross-sectional area. Now I want to determine the wetted perimeter. So it's going to be the angle times the diameter, 1 foot, divided by 2. Okay, so the left-hand side of the equation will be area to the 5/3 divided by wetted perimeter to the 2/3. Here's the area to the power of 5/3. And then divide that by the wetted perimeter to the power of 2/3. Left-hand side is pretty small at this point.
I think you put 5/2 instead of 5/3.
Oh, good catch. Thank you. All right. 5/3. All right. So the difference between the right-hand side and the left-hand side, and we want to goal seek so that the difference is 0, and then that'll tell us what is the angle at that minimum flow rate. So data, what if analysis, goal seek. So we want our difference to be 0 by changing the angle. Okay? And it says that the angle will be 2.11 radians at the low flow rate. And so from that we can determine the flow depth. So the diameter, which is 1 foot, divided by 2, times 1 minus the cosine of this angle divided by 2. So the flow depth would be 0.255 feet, but there's one more correction we have to make. Does anybody know what it is? Manning's N. Yeah, so all of this was assuming that the N value was 0.013, but it's going to be higher than that because the pipe is only about 25% full, according to our best guess so far. So when the pipe is 25% full, then we go over from, let's see, it'll be the middle here. We go over, and that's where the biggest difference occurs between Manning's when it's partly full and when it's completely full. So if I go up with that, I think that's about 1.27. So 1.27, the full value. So what we're going to have to do is 0.013 times this correction factor. So instead of using 0.013, I should use 0.01651 for the end value because it's not flowing full. So I have to correct that, 0.01651. So that's going to be the end value when it's only partly full. And that changes our estimate of the angle. You'll see that the difference has deviated from 0 because of that adjustment to the end value that was just made. So again, I have to run through goal seek. And I won't do this 3 times like I did before. Let me just go through this 1 time. So we want the difference to be 0 by changing the angle. All right. Unfortunately, it's a more modest change. It's just saying it's going to be, instead of 25% full, it's going to be 29.4% full. And that still puts us about in the same range on this curve. It was a flat section where vertically you don't get much change in end value from an adjustment in depth. So we don't have to iterate through another time, but here is going to be this is the flow depth at Q min, where we have iteratively corrected the n value for partial depth. All right, the last part of this is just evaluating what is the flow velocity at the minimum flow depth. And the way that we can find the velocity is Q divided by A. So we know the flow rate going through the pipe at minimum. It is this 0.45 CFS. Okay, so it's Q divided by the area under minimum flow conditions, which we've just calculated. So we had cubic feet per second for our flow rate, and here our area is in square feet. So that's going to give us the velocity in feet per second. So it's going 2.34 feet per second. And our guidelines say that the minimum flow velocity should be above 2 feet per second. So I think we're going to be okay. It'll keep the solid suspended. It'll help the limit the amount of maintenance that's required in this sewer. But, I mean, the greatest factor that dictates that flow velocity is the slope. And unfortunately, that's a parameter that the designer doesn't ultimately have a lot of control over. The slope is, in some parts, it's dictated by the elevation of the ground because, although the pipe is underground, if you have it at a different slope than the ground slope, then the pipe will either be getting deeper or closer to the surface. And so sometimes if it's completely flat ground, we're talking like Kansas type flat, they'll still have a slope to the sewer pipe, but then they'll have those pressurized lift stations that I was talking about on Monday. But in this case, the 0.75% slope is adequate for us to stay above the required minimum velocity. So that is the sewer design procedure. Now, in the 3 minutes that remain, I want to tell you about hydrogen sulfide. It's a poisonous gas that can form when wastewater is degrading under anaerobic conditions. That means if there is not enough oxygen in the water, then the waste begins to decompose by bacteria that consume the energy in the waste, but they do that without oxygen as an electron acceptor. So if sewers move slowly, then another problem besides sedimentation, another problem with slow-moving sewage water is that that's more prone to anaerobic conditions that cause this poisonous gas, hydrogen sulfide. It's also corrosive, and it can cause premature degradation of concrete and the reinforcing steel manhole covers. So there are empirical equations that estimate the potential for the formation of hydrogen sulfide, and those equations take into account both the hydraulics, so you can see the flow rate, the wetted perimeter, the width of the water surface at the top of the pipe, the slope, but also something known as the effective BOD. And I think probably everybody in here has taken environmental or is either taken it or is in it this semester, right? Do you already know what BOD is? Biochemical oxygen demand? Well, this effective BOD is just adjusting for the temperature of the wastewater. So you'd take the BOD at 20 degrees and then you'd empirically adjust it depending on what the temperature of the wastewater. And typically wastewater would be about the same temperature as the home that it's coming from. And so it may be that the wastewater is warmer than 20. So when you calculate this hydrogen sulfide potential, you can find if the Z value is less than 5,000 that it would be uncommon for hydrogen sulfide to form. There's an intermediate range where it's possible, and in any case, people who are going down into maintained sewers need to work in pairs, have someone who can rescue the worker that's working down there. They have hydrogen sulfide detectors. But if the Z value is above 10,000, then it's likely, and that would mean that you need to be especially careful. And from a design standpoint, you try and change it so that you increase the slope and reduce the Z value. Because if you do this at the design phase and you're predicting that there's likely to be hydrogen sulfide formation, then the sewer system isn't going to last as long as it should be. So it's something that you can maybe take into account during sewer design. Okay, well that is all the time we have for today. I'll just leave you with the reminder that Friday's class is online. The assignment you have that day is due by 5 o'clock, and then the final exam will have a week from Friday, so on the 29th. So thanks for a great semester. I'll see you for the final exam, and if you have any questions in between now and then, just let me know.